Interesting. Oh, here we go. This just didn't connect. There we go. Your old friend, the uncertainty principle from modern physics, when people say the uncertainty principle, they mean sigma x, sigma p is greater than or equal to h bar over 2. But this allows us to generate a similar uncertainty principle for any two operators, right? So any two dynamical variables for which there are some associated operators. So here I'm thinking of some generic dynamical variables A and B, and this says the same thing. Now you have to unpack this. This means you have to take the commutator between those two operators associated with the variables. Then you have to take an expectation value of that operator, and that's in most cases going to depend on the state you're thinking of. So what this statement says depends on what state your particle is in, and as the state of your particle changes with time, this right-hand side might change with time because the expectation value of an operator isn't always constant, right? Expectation value of energy might be constant, but other operators may not be constant. And so, that's going to depend on the state that we're in. So we showed how the usual thing comes out for here. And in cases where the operators commute, easy case is if you have x operator and the x cubed operator. X cubed operating on any function of x is just multiplication by x cubed. Those two operators, they can move right through each other, and therefore the right-hand side is 0, and that means the product of the uncertainties is greater than or equal to 0, which tells us nothing. So we don't really get any information in that case, even though it seems like something good is happening when they commute, but actually it gives us something where we don't get any information at all, because just because it's greater than or equal to 0 doesn't mean it's equal to 0. It could be any number. The left-hand side has to be non-negative, and all it's saying on the right-hand side is that it's non-negative. Incompatible observables means observables that don't commute, and compatible observables are ones that do commute, and we'll talk about the importance of that in just a second, but let's do practice with a worksheet trying some other operators. These two operators definitely don't commute. It's a good time to practice calculating commutators. So one operator is the second derivative operator, and the other one is the position operator. So it's somewhat related to the momentum and position operator, but not exactly. By the way, this, if you're on Zoom, this is on, I believe, today's date. It's the first of the 3 worksheets that I posted on there. I don't guarantee that we're going to get to all 3 worksheets, but I wanted to be prepared. So let's just answer A together. Are these operators both Hermitian? You're not supposed to prove this. You should have in your head now kind of what the common operators are that are Hermitian. Is the derivative with respect to x Hermitian? No, it's not. I need that I out in front of it to make it Hermitian. And that's from the integration by parts that gives you a minus sign when you go to the other side. Having an I next to it gives you another factor of a minus sign, which cancels each other and makes it the same operator on the other side. But for the second derivative, I don't need an I. For the third derivative, I do need an I. For the fourth derivative, I don't need an I. So every other derivative needs power or order derivative needs an I next to it. Similarly, any function of x, where you mean, the operator is just multiplication by, say, sine of x or something like that, that's going to be Hermitian automatically. If I put an I in front of it, it's not going to be Hermitian. So the answer to A is yes, they're both Hermitian. We've already shown this. I think we made a verbal argument about the second derivative, right? When I pull one derivative over to the other side under the integral, for which we're checking hermiticity, you get a minus sign from integration by parts. But then when I pull the other derivative over, I get another minus sign, and I get back to the same operator. Yes? The following operators are Hermitian, And if we don't have the I's there, or if we have the I's in the wrong place, they wouldn't be Hermitian. So I ddx is Hermitian. ddx by itself wouldn't be Hermitian. The second derivative is Hermitian. Well, of course, you know, this is almost the kinetic energy operator. If I had a minus h bar squared, you know, minus h bar squared over 2m times this, then that would be the kinetic energy operator. So this is related to the kinetic energy operator. But for the third derivative, I would need another I out in front. Fourth derivative, no I, and so on. All functions of x, real functions of x, I should say, not all functions of x, but you know, any normal function of x, x, sine x, x squared, all of these are Hermitian, but you know, something like I times sine of x is not Hermitian. So that I is gonna get a minus sign in front of it when you bring it under the star on the other side of that inner product that comes into the definition of Hermitian. So yes, d squared dx squared is Hermitian and x is Hermitian. If you're not sure about that, it's a good exercise on your own time to just try to prove that to yourself and remind yourself what happens. Because, you know, perfectly legitimate question on the next exam would be, here's an operator, not too complicated. Is it Hermitian or not? And maybe I ask you to prove it, or maybe I don't. Maybe I say, here are 5 operators, circle the ones that are Hermitian. Right? That may have been something on the example exam that when you look at that. So know how to just sort of look at common operators and know if they're Hermitian, but you should also know how to prove that they're Hermitian if you're told to do that. Another question?
So like you said, you can add like negative or constant, it's supposed to be Hermitian.
That's right. So I don't really care. We know the momentum operator is minus I h bar ddx, but putting the minus in the h bar there doesn't do anything because a minus sign can go underneath that star on the left side of the inner product without any problem, right? When it's i's that switch signs, right? So here I get a change in sign from the derivative when I do integration by parts, and I get another factor of change in sign from the I, and they cancel each other and give me the same operator back on the left-hand side. Okay, so this is sort of a long worksheet, but you know, try finding the commutator of these operators just so you know what to compare with. I find the commutator in this order, d squared hat x hat. The commutator is 2d dx. So if you're not getting that in part B, let me know and we can sort of look at your work. Well, I just said find the commutator of the operator, so I didn't specify. So it was a 50-50 coin toss for me. That's just how I chose it. Maybe you want to do it the other way because I wrote them down in the other order. But you know, the commutator in the other order is just the negative of that. Always, when you switch the order in a commutator, you just get a minus sign. But one thing to notice is it's not Hermitian. The commutator of 2 operators is not Hermitian. It's something called anti-Hermitian, which means you exactly get a minus sign when you take the Hermitian conjugate of it. Jake Woosley, I don't know if you heard, but we're working on the first worksheet that's posted under today's date on the website.
Yeah, I did.
Okay, I want to do B together. Just you may be just about done with it, but just to make sure we're all on the same page, because there was a question about this. So the operator that we denote by the commutator between the second derivative and the multiplication by x operator. This is an operator, and we're going to mess things up or forget some terms if we don't let it operate on some generic function f of x, because there's some product rules that are going to come in on there. Operators are always operating on functions of x, and so in order to work out what this is, we need to put a generic function of x next to it. Okay, so let's write out the definition. So we first do them in the order that they are written, d squared dx squared of x f of x minus x, the reverse order, this one first, then this one, d squared dx squared of f of x. Okay, and then I simplify, and again, I'm going to have to do some product rule stuff here. Unfortunately, I got a second derivative that I got to do a product rule. Let's do them one at a time. So let's work out what this piece is. Let's do the product rule for one derivative. So what I get is the first one times the second one's derivative plus the second one times the first one's derivative with respect to x, and that's 1. And then let's do it again. Let's apply this other derivative onto there. So I get another product rule here. So just applying this to the first part, I get the first one times the second one's derivative. Oh, I'm sorry, and I should, for the sake of the video, unshare the screen. First one times the second one's derivative plus the second one, second one, df dx, times the first one's derivative, which is, again, is 1. Okay, so that's expanding out this part. And then I also have to apply it to this, plus df dx. Okay, so that's this part, and then, well, if I just put the rest of it in there, I have minus x d squared f dx squared. So I get a cancellation, and you always get some sort of partial cancellation in this stuff when you're doing this. And so what I see is I get 2 times the derivative of f with respect to x. And that's what this operator is applied to f of x. And so this simplifies down to 2 d dx f of x. And therefore, this is what I'm calling the commutator between d squared and x, 2d dx. It's going to become painful doing those product rules if we go to a third derivative, but at least that gives you the idea of the general kind of, we don't see too many third derivatives anyways in quantum mechanics. Okay, are they compatible observables? No, they're not compatible. They're incompatible. Compatible just means the commutator is 0. This is not a 0 commutator. Commutator being 0 means you get the 0 operator. The 0 operator means you multiply by 0 and you get the 0 vector when it operates on. Okay. Let's figure out what the generalized uncertainty principle says about this product of uncertainties. Sigma d squared, sigma x is greater than or equal to, and remember I said we can always take the square root of both sides as long as we put absolute values on the side. So I'm going to use the part that is already square rooted, because we had a bunch of squares in Griffith's form. This times the expectation value of d squared x, that commutator, absolute value. Okay, so I've got to calculate, I know what this operator is now. Now I've got to take the expectation value, and the expectation value always depends on what state you're in, or in most cases it depends on what state you're in. So I have to use the state that's given. It's a Gaussian function, a e to the minus ax squared. So let's calculate this expectation value. It is the integral from minus infinity to infinity. Remember, I sandwich it between psi star and psi, my operator, and integrate. So psi star is a e to the minus ax squared. It's purely real, so I don't need to do a star, times 2 ddx operating on a e to the minus ax squared and integrate with respect to x. And, well, of course, the 2a squared can come out in front. 2a squared. What I have to integrate, well, let's see. When I take the derivative of this, I pull down, when I take the derivative of e to the u, I get e to the u times the derivative of this with respect to x. So I pull down a minus 2ax. So it looks like I get the integral. Tell me if I'm making a mistake here. I pull down a minus 2ax, and I get an e to the minus ax squared back again, combined with this one that I had out there, gives me an e to the minus 2ax squared, I think. Okay, and then I go to my, so, you can factor these constants out in front. So I have x times e to the minus a constant times x squared. And I look at my Gaussian integrals, which are on, well, in this case, I don't need to look at my Gaussian integrals, right? Why? It's an odd function, symmetric limits. So this integral from minus infinity to infinity is 0. Okay, so we get kind of something that you should regard as not interesting. We've just found out that sigma d squared, sigma x has to be greater than or equal to 0. But we knew that before we started. That's always got to be true because those are non-negative. These things can't be negative and they're always real. So nothing much to say right there. Right, that's the answer to C. Okay, now we could do, let's just talk through D and E, maybe without doing the work. You can tell me if you want to do the work, but you have to, you can see from the space there, you got to do a little bit of work. Let's find out, we just found out what the product of these two things has to be greater than. It wasn't very interesting. Let's now calculate what sigma x is and what sigma d squared is. When I calculate sigma x, again, I have to calculate the expectation value of x and the expectation value of x squared. And then I'm going to use the fact that sigma x is equal to the square root of the expectation value of x squared minus the expectation value of x squared. So I have to calculate those two expectation values for this particular Gaussian state. And expectation value of x, I think, is pretty clear. What will that be? It's going to be 0, because our state is a Gaussian function that's symmetric around 0. And so the average value of x is going to be 0. So, you could write it down and you could use a symmetry argument for the integral, but we expect that one to be 0. This one's not going to be 0. I'm going to get an x squared times a Gaussian function, and I'm going to have to use my x squared times a Gaussian function integral in order to work it out. I'm just going to tell you what the final answer is. And, oh, I don't even have the final answer written down here. In any case, sigma x is definitely not 0. It's some number greater than 0. It's even more work to figure out what sigma d squared is. Why? Because I have to sandwich that second derivative between two Gaussian functions, and then I have to let two derivatives separately apply to the Gaussian function. In the second one, I have to do a product rule. It's kind of a pain. There's nothing hard about any step. It just ends up being a little bit of a mess. But if you work it out, this one's also greater than 0 in that state. And so we're seeing here that, sometimes people look at this and they say, oh, well, one of the, the product of these has got to be 0. No, it's got to be greater than or equal to 0. I mean, here's a case. We chose sort of a random state, this Gaussian state, and the product of those two is some positive number. So it's not close to 0. It's possible if we chose just the right state, we might be able to make the product of the uncertainties be 0. But this is not the state. That's all we've shown right here. Okay, and the last question says, considering that neither of these uncertainties is 0 for the state given, is the product as small as the generalized uncertainty principle allows? No. Is this a problem? No, that's what we should expect. And in this case, the answer to C, the fact that this is 0, wasn't really dependent. I'm sorry. In C, I'm trying to understand my last note there that I didn't look at before I came to class. It is possible to show that the answer to C being the statement of the generalized uncertainty principle, is the same for any real normalizable differentiable function psi of x. In other words, it doesn't depend critically on the shape of this function. I can't remember if I assigned that as a homework problem, but at some point you might find yourself proving that fact. It's not too difficult to prove. Okay, just wanted to give an example of a more generic case that you weren't familiar with, and this is how you turn the crank and go through there and find out what the generalized uncertainty principle says. A couple of you in reading responses asked about technical details that I believe were in the derivation of the generalized uncertainty principle. If you want to know more about that, we can talk about them in office hours. Come by, and if you're interested in how he makes some step. To me, it just didn't make the cut in terms of insight and excitement to go through the derivation of the generalized uncertainty principle. But if you want to talk about it, I'm happy to do so. Okay. Let's go back to the slides here. So again, incompatible observables means they don't commute. It's just a different name for it. In a homework problem, I think this is in somewhere in 9 through 12 that you're going to do before the exam, since the generalized uncertainty principle is our last section that's going to be covered on the exam. you will show, and it's not too hard to show, and I sort of point the way through a proof, that if you have incompatible observables, there's no way that we can find a common complete set of eigenfunctions. In other words, a set of eigenfunctions that are eigenfunctions, each one is an eigenfunction of both operators that are incompatible, we're assuming here, such that the collection of all those states are a complete collection of vectors. Okay, we're interested in complete set of vectors because they're going to form kind of our basis, right? The thing where we're going to expand an arbitrary state in terms of those. And that's sort of nice. And if you have any Hermitian operator, we know from the generalized statistical interpretation that we can get a complete set. We just find the eigenfunctions of that operator and they form a complete set. But now we're talking about if we have two operators, is it possible that we can find a set that's complete and is simultaneously a set of eigenfunctions of the first one and the second one? And the answer is no, if they don't commute or if they're incompatible. That means the same thing. However, if they're compatible, we can find them. Here's a trivial example of compatible operators. Momentum operator, and that we might call this the kinetic energy operator, right? P squared over 2m. Those two operators commute. We already showed that the momentum eigenstates are states like e to the I kx for any k between minus infinity and infinity. If I choose a particular k that corresponds to moving to the right, and I take the corresponding negative k that makes it go to the left with the same wave number, that means the same wavelength, but traveling in different directions, those are two different momentum states, but they have the same kinetic energy value. So they're both, each one of those states is a definite momentum state, and it's also a definite kinetic energy state. But in this case, there is a degeneracy for the p squared over 2m. I can find two linearly independent states that have the same kinetic energy. The one going to the left with a certain k, and the one going to the right with a certain k, and to the left with the corresponding negative k. They both have the same kinetic energy because, intuitively kind of you're squaring it away. But okay, if we looked at those states, the claim is those are states of, they share a complete set of eigenfunctions. I could talk about the set of eigenfunctions of the momentum operator, and we're talking about the same set of eigenfunctions of the kinetic energy operator. And if we look for each one of those states, what the probability density is as a function of momentum and the probability density as a function of kinetic energy, we can see that for each one of those states, there's just a delta function at one location. So they're states of definite momentum and definite kinetic energy. You have incompatible observables, and the iconic incompatible observables are position and momentum. They don't commute. Now, based on this worksheet, I just want to summarize three different cases that happen. Sort of the nicest case, that's the one we were just looking at, where two operators are compatible, or the dynamical variables associated with them are compatible variables. And in this case, we get no restrictions on the uncertainty, so it's sort of a boring uncertainty relation. And in this case, you can find states in which the uncertainty of one observable is arbitrarily small, or both observables is arbitrarily small. Although if you choose a random state, it's probably the uncertainty in each one's going to be perfectly finite. So that's kind of the best case scenario regarding simultaneous knowledge of the observables of A and B. Two variables commute. You can put a particle in a state such that the uncertainty in each of those variables is 0. Here's the case that happened for position and momentum. The commutator between position and momentum was a number, right? It was IH bar. And so, in terms of an operator, we're normally thinking of the right-hand side as an operator. This is the operator 0. It just when it operates on a function, it turns it into the 0 function. This If I think of it as an operator, a number is just a multiple of the identity operator. The identity operator doesn't do anything. Okay, we would still say in this case, we would say that A and B are incompatible because they don't commute, right? It's not 0 over on the right-hand side. In this case, we found out when we looked at the position momentum uncertainty principle that it doesn't matter what state we're in. Regardless of the state, there's some lower bound that's given by this generalized uncertainty principle. In other words, this side doesn't depend on what state the particle is in. And so that's kind of the worst case in terms of simultaneous knowledge of, say, position and momentum. The more you know about position, the less you know about momentum. And that's true regardless of the state that we're talking about. We can make a generalized statement. The example that came up in the worksheet that you just did, where we found out the commutator of our two operators was 2ddx, that's neither a multiple of the identity, nor is it 0. It's like just a regular old operator. So we took the commutator and we got a generic operator. So in that case, we would still say they're compatible, but it's sort of intermediate between these two states. We find in this case that what the generalized uncertainty principle says about these two operators depends on the state that it's in. And you may, as that state changes with time, you may find that the product of the uncertainties changes with time. At some periods of time, it's bigger, and in other periods of time, it's smaller. Sometimes for a moment, it might go to 0 and then be not 0 later on. So it's sort of an intermediate case there. So those are kind of the 3 cases. Okay. The energy-time uncertainty relation, I'm not going to say too much about it, but Griffiths makes a big point about it not meaning the same thing. In other words, you can't get this from the generalized uncertainty principle. It's sort of a rule of thumb, and you got to know what the rule of thumb is saying. Okay, so you saw this probably in modern physics. Delta E, delta T is greater than or equal to h bar over 2. So here's what Griffiths says about it. Time is a special thing in non-relativistic quantum mechanics. We don't treat position and time on equal footing like we do in relativity. This is a non-relativistic theory. It's based on the non-relativistic kind of definition of kinetic energy as p squared over 2m and so on. There's no gammas in there. So it's not an operator. It's sort of a parameter that tells you how things change as that parameter is changed. And therefore, this relation has a different meaning than delta x, delta px is greater than or equal to h bar over 2, despite the similarities, and despite the fact that if you know anything about special relativity, you know that E is to P as T is to X, kind of. They're both of those are parts of the same 4 vectors. If you take more special relativity at some point, you'll learn about 4 vectors. So here's what Griffith says. The meaning of delta E is the same thing as the uncertainty in the Hamiltonian. It has the usual meaning here because the Hamiltonian is a legitimate operator. But delta T is different. This is what it's defined to be. Choose a dynamical variable, Q, and we're going to define delta T to be the uncertainty in Q divided by the magnitude of the rate of change of the expectation value of Q. You can think about the fact that, the D expectation value of Q, well, you can think about the units that are going on there and the fact that that makes sense as a time. Okay, so the interpretation of this delta T is the amount of time it takes the expectation value of Q to change by 1 standard deviation. If you think about this is the rate at which it's changing, here's the amount it's going to change. So you can think of, distance equals this rate times some amount of time. We're just solving for the time. And what Griffiths points out is that it can depend, and usually does depend, on the operator or the dynamical variable Q that you choose. And so for different Qs, you're going to get different delta Ts. And so that makes it seem not like such a precise statement there, Choose your Q to be momentum, you'll get one thing. Choose your Q to be position, and you'll get something else, right? And form your favorite dynamical variable. But in any case, the upshot is, one thing it is definitely saying is that if the uncertainty in energy is really small, that means you're almost in a definite energy state. If the uncertainty in energy is really small, then the uncertainty in time is large. And remember, the interpretation of this is how long you have to wait for an expectation value to change by a certain amount. And what it means is all the expectation values of all operators have to change slowly if you're in an approximate energy eigenstate. Okay, I'm happy to talk more about that. Several people had questions in reading responses, even way back when we first talked about the uncertainty principle having to do with that. But when you find out the details here from Griffiths, it's kind of disappointing to think, well, it really doesn't say one thing. It says lots of things depending on which operator you choose there. But the one thing that it does say is if you're in almost an energy eigenstate, every expectation value of every dynamical variable is going to change slowly. So that's something universal that it's saying. Questions before we go on? Griffiths at this point mentions an incorrect way to interpret this, that you sometimes do hear people say that somehow this is saying that energy is not conserved. You can have a change in energy for a very short amount of time. You can have a big amount of change of energy, or for a modest amount of time, you can have a modest change in energy or something like that. And he says that that's definitely not a correct thing to say. So people sometimes say something like this: energy delta E can be borrowed as long as it's paid back in time delta T. So the energy is changing. And so, I put this little one-page thing in the notes just because it raises the question of, well, what does energy conservation mean in quantum mechanics? Griffiths says there, energy is definitely always conserved in quantum mechanics. And someone who's a high school physics teacher once asked me, is energy conserved in quantum mechanics? And so I wrote this thing up based on that. So let's just think about this, because I don't think we've raised this question before. We know, at least for certain types of conservative forces, that in classical mechanics, energy would be conserved in an interaction, right? If you have electric repulsion between charges, the energy is conserved. As you decrease the kinetic energy, you increase the potential energy by the corresponding amount. What about in quantum mechanics? Well, there's a sense in which yes is true, but there's a redefinition of what energy conservation means. So you really have to explain to not be misleading. Certainly in classical mechanics, a system, there's no uncertainty in anything when there's only one energy that, say, a particle has at any one time. Or if you have a collection of particles that are interacting via forces, you add up the kinetic energies and the potential energies, and there's a certain well-defined energy that it has. And either that total energy changes with time, in which case we would say energy is if it changes with time, energy is not conserved. And if it doesn't change with time, we say energy is conserved. In quantum mechanics, that's not true generically. A system usually doesn't have a well-defined energy, unless it happens to be in an energy eigenstate. But generically, it's going to be in a linear combination of energy eigenstates. Now, if it happens to be in an energy eigenstate, there's only one possible energy measurement outcome, and that doesn't change with time. So in that case, we would say, oh yeah, it's just like the classical case. There's only one possible energy you're going to measure when you measure energy, and it's not going to change as time goes on. So that seems to be the same thing. But more generically, it's not in an energy eigenstate. That means it's in a linear combination of several energy eigenstates, and there are several possible measurement outcomes. And the outcome probabilities don't change with time. That's one of the things we found back in chapter 2. But still, measurement outcomes can be kind of lopsided for a while. For example, if I am considering, the infinite square well, to go back to one of our simple cases, and I say, let's consider an initial state at time t equals 0, which is equal parts ground state and first excited state. Okay, definite energy states, both of those. So the probabilities of being in the ground state and first excited state are both 1/2 when we square those coefficients. And let's imagine we prepare 10 identical systems and we measure the energy for each one of those systems. It certainly is possible that for that collection of 10 systems that we get E1, the ground state energy for all 10. Now, that's not going to go on forever because we're saying the probability of each energy is equal. Still, when you flip a coin 10 times, it is possible to get heads all 10 times, right? And you could calculate how unlikely that is. It's quite unlikely. 1/2 to the 10th is a pretty small number, but it's certainly possible. So these things can be lopsided for a while. So would you say then, in that case, is energy not conserved or is it conserved? Well, we need a definition of what conserved means in quantum mechanics. And generally, the definition is that if the expectation value of an operator doesn't change with time, that's the closest thing we have to the classical analog in quantum mechanics. If the expectation value of an operator doesn't change with time, we would say it's conserved. And this is something that is always true in quantum mechanics, right? The individual probabilities aren't changing, and therefore the expectation value of energy isn't changing. I'm assuming we're not making any measurements in the intervening time. We're just letting it evolve according to time-dependent Schrodinger equation. Okay, so yes, people say it's conserved, but it means something different. This is what it means in quantum mechanics, that the rate of change of the expectation value of energy is 0. And in fact, the rate of change of the magnitude squared of each of the coefficients in front of the definite energy states don't change with time either. Okay, that's the end of section 3.5. Where are we time-wise? 28, okay, good. Any questions on that before we do a warm-up worksheet for the next section, which is just kind of for fun, and it will help raise some questions or maybe relieve us of some questions that, I just found when I first started teaching this course, people would be really confused about what rules they could use. So we're going to start talking about this abstract, what's called the Dirac notation for vectors, where we have the little line and the angle bracket. And here are just some questions about, I think this is worksheet number 2 posted on the website for those of you on Zoom. So take a look at that. There's not much work to be done here. I'm just asking in words, what's the difference between this and that? So let's spend a few minutes doing that. Okay, so these are mostly just supposed to be set out in words. Can anybody explain to me what the difference between the two things in part A is? Fn and this, it would be the same thing as if I said psi n and psi n as a function of x. Is there any difference between those? Not much. There is a subtle difference. They're describing the same vector, but this is sort of like saying, is there any difference between me giving a name to a vector? So I could say, I'm going to define it just geometrically. Something is moving in that direction at 3 meters per second. So I've defined it without reference to any axes or anything. Is there any difference between that and giving the x, y, z components? Once I've told you what the direction of x and y and z are and where the origin is, right? Then you can give the components of that vector.
I'm thinking that the left one, like this is just my inference, but that the left one defines the vector as a vector, or at the very least puts more emphasis on it as a vector.
Well, that's right. So we're thinking of there's one vector, and there are lots of different ways to express that vector, right? And each one is sort of dependent on some basis, right? So we already talked about if you have a vector, you could give its position representation of it, but I could also give the expansion coefficients in terms of the psi n's, right? I could give those Cn values, and we already said that's a perfectly good alternative way of expressing it. It's somewhat analogous to saying, there's only one vector v, but I could write v, well, in fact, here's a good picture that goes along with that, right? I have one vector v. I'm talking about that vector v. There's only one of them. But if I give its components in the x1, y1 basis, that's going to be different than its components I'll get in the w1, x1, y1. There's supposed to be an x2. Otherwise, the pattern doesn't fit. x1, x2, w1, w2. The components would be different in those two bases, right? I'm going to get different components. So it's going to look different, but we're talking about the same vector. So this is like a universal name for the vector, and this is like a specific way to describe it. When I give you a universal name, sometimes you might say, well, I don't know what you're talking about. You just wrote down the vector v. How am I supposed to know what that one is? And I might say, well, in this coordinate system, here are the components. That's how I communicate the real information to you. But this is supposed to be a notation that stays the same, independent of any basis. It just refers to that vector. Whereas the second one to the right refers to a very specific, position representation, we would say here. Rather than a momentum representation, I could give the momentum space wave function, or the energy representation, that would be giving the CNs for a particular potential, or so on. So there's a slight distinction, but they're supposed to be the same thing, really, here. What rule would or would not allow me to change the first one into the second one in B? I put this on a worksheet because this is something you'll see in Griffith's textbook. He labels a vector by that big, cumbersome thing. And then the question is, can I do something like this? Bring this outside the vector. The CNs are constant. So, again, we don't have the liberty of making such ridiculous labels, right? Everything that goes inside here is a label. And because of this, we have a lot of space inside this new label. We can put big, ridiculous things that we probably wouldn't do if we were just using the arrow notation. And so people do take advantage of that, but you got to remember that this is a label. And it's supposed to be reminding us of the vector that results when you do this. So I would say these are exactly the same. In this case, they're both abstract vectors. This one's telling me a process, right? I do this to a vector, I take an infinite collection of vectors Fn, and I add them up in this way, take this particular linear combination, and I might say, this is what results. Why did I label it that way? To remind me that this is where it came from. So we're not used to doing this with vectors because we didn't have such a good big labeling space. But you'll see Griffiths write things like this, and then he'll willy-nilly go back and forth like this. And you got to know that there's no special rule. It's just that this is a notation. The whole reason it's a good notation is because it reminds me that it came from this. That's the process I use to get the vector with that. So I would say really there's no difference there. What about, so here we're bringing in an infinite sum. Can I do the same thing with a vector Q that's acting on, what did I call it here? Psi. Sometimes you'll see Griffiths maybe or maybe not do this, or at least raise the question. Is there any difference between those two? No, same idea, right? This is just a big complicated symbol. And the whole point of that complicated symbol is to remind us that it is the vector that results when Q operates on psi. You get this vector over here. So there's no difference between the two, right? Because this is, the vector we're talking about here is the result of this operation. So they're exactly equal there. What about the 3 at the end? Are they all the same? Yes, if Q is Hermitian, so if you buy this, the first two are always the same, irrespective of Q is Hermitian or not. And they're equal to the third one if Q is Hermitian, but otherwise I would need a dagger on Q over there. If I put in the third one, the rightmost one, a dagger on the Q, then it would be true for any operator whatsoever. All three would be equal, but it's only true here that the first two are equal to the third one in the case where Q happens to be a Hermitian operator. Okay, I'm bringing this up now because next Monday, we're going to start dealing a lot with Dirac notation and really becoming comfortable with manipulating things, and makes things very efficient to change things around. So it's going to be very nice, but you're going to see things like this, and you'll find when you do the reading in Griffiths, which you will do before Monday, you'll see him being kind of fast and loose sometimes with that notation. And he's assuming, I guess, that you understand that, hey, it's a notation. Why else would I name it that? Unless it's supposed to remind me of the obvious thing that's happening to a particular vector or set of vectors. All right, great.